Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video we'll speak about a bias and variance decomposition. We can decompose the generalization error of a learner into the bias of the learner, variance of the learner, and some noise which is inherent to the data that we can't really reduce anymore. You will see a simulation study, a small demonstration, and we will close with some comments on capacity and overfitting. The generalization error of a learner I or of an inducer I is the expected error of a model trained on sets of size n and evaluated on a fresh test sample. So it's very important here in this entire chunk to be clear about the difference between model and learner. And the output of a learner is a model, but the learner itself is not a model. Okay? So if we feed some data set dn into the learner, the output will be in a learned model f hat, which we denote with subscript dn here to make clear that we used the data set dn of size n to learn that model. Okay? And the generalization error of an inducer or of a learner is then basically the expected loss, so it feels like a risk. So we have an expectation of a loss, but we take this expectation over a lot of things. So on the one hand, we take the expectation with respect to the fresh test sample where we evaluate on, so x, y, but we also take the expected value over, and that's a new part here, over the training data sets that we used to train or to learn the model. Okay, so this is a double expectation. We, instead of like this longer subscript, we can use a somehow smaller subscript, which means the exact same thing. But the important thing is, as we say here, that the expected value is, or the expectation is taken over all the training sets and independent test samples. So perhaps it is more intuitive, not sure, if we frame this as expected risk and expectation over the different training data sets that we can use. So same thing here, left hand side. We can, okay, let's clean that up. We can write this also as this double expectation. So we take the expectation with respect to the new test data and the training data that we use to train the model. But if we do that, then the thing that is here inside this outer expectation is really just the risk, right? It's just a kind of normal risk of this model f hat dn. So it's just the expected loss of that model. But the new thing is here that we don't say that the model is already fixed, but that we can use different data sets dn to train that model, which means that the risk itself is a random variable because the model f hat is a random variable because this data set is random. Okay? So this randomness leads to the risk being a random variable, which means we can take the expectation of that random variable. So these are a lot of layers here, but I think it's important to have it that clear, because then you see that the generalization error is something related to the inducer, to the learner, while the normal risk is related to a fixed model. Okay? So risk is something we take of a model, but if that model is random, then we can also take the expected value of that thing here. And the interpretation is, well, which error do I expect from a given learning algorithm? So it's just about the learning algorithm. If I feed data that I don't know of yet to it, and I only know the size n. Okay. So, long explanation, but I hope that helped. Now, the slide has a second part. Now we just look at the L2 loss. If we just look at the L2 loss, we can decompose this generalization error into 3 components. You will see the formula on the next slide, and we have an entire deep dive that proves that that formula is actually the decomposition of the generalization error. So we assume we have a data generating process, we have some true model f true x, and an additive zero mean homoscedastic error, epsilon, and that error is independent of x. And then we can have this decomposition. Similar decompositions exist for other losses, and you can see, or you can look at this Brown and Ali 2024 paper to see more about that. But for now, we just stick to the L2 loss, where we can do this additive decomposition. So this is this additive decomposition of the generalization error of the learner. We have 3 components. The first component is just sigma squared. It's just the noise variance. So it's really just the pure variance, the pure noise epsilon, or the variance of that pure noise. We can also call this base error, intrinsic error, irreducible error, and whatever we do, we will never be better than that. Means that no matter how good our training algorithm is, we can't reduce the inherent noise to the data. Okay? We can just try to make the best out of it, and we can try to reduce the other 2 components, but not this first component. Then the second component, expectation of the variance of f hat dnx given x. This thing here, inside that expectation, is the variance of the learner at some point x. Okay? So we fix a point x, and we ask ourselves what happens if we sample new data again and again and again, new training data, dn. What happens to the variance of the trained models at this specific point x if we train on other data sets? So this term here tells us how much the trained model fluctuates at test x if we vary the training data. What we do then in the second step is we average over the entire feature space. Okay, but that's 2 independent steps. First we compute the variance at each x, and then we take the average over the entire feature space. This thing here tells me about the learner's tendency to learn random things irrespective of the real signal, so how much this overfits to some data points. So because it means, okay, if just some data points are different and then the model is very much different than before, this means we are capturing too much overfitting here. That was the second part. Now the third term, that's that one here, the longest. Let's decompose this as well. So, no. Let's start with that part here. Expectation of the data sets of f hat dn of x. This thing here is some average model integrated out over all the n. This part. So this means we can have a lot of models, and we just take the average over all these models, then we have an average model. And with this difference here, we look at some specific point x. How far is this average model off? So how bad are we on average, but at this point x? Okay, so we have a lot of averages going on here. How off are we on average? Average over the models, or average over the training, the different training data sets. We get an average model. How much are we off, but at point x? Okay, because then later we square it, And then we take the expectation over the feature space. So that's a second average. So we average out this squared bias over the entire feature space. Okay, so perhaps just one comment here. Models with high capacity have low bias and vice versa. So if we are able, or if high capacity means the hypothesis space is rather rich, we can fit like whatever we want, right? So we have a low bias, we are able to find a true model, but well, you will see later that this is a trade-off with the variance. That's why it's called bias-variance trade-off. And if you have a low capacity, the bias will be higher, but then the variance is smaller. Okay, that is so far for the theory. We could profit from some examples here, right? So, simulation study. We have a true model. Well, that's just a squared effect here of x. We have an additive error, in this case Gaussian 0, 1. We have some data points here and we split them into train and test data points. So these orange, I think, triangles are the test data points and the blue dots are training data points. So far, so good. So what we want to do now is we want to estimate this bias term and this variance term, right? So we do this via bootstrapping of the training data. So we keep the test data fixed. Let's go back. So we have these 8 test data points. We don't touch those. We only bootstrap the training data. And we could have used Monte Carlo integration here as well, but we think bootstrap might be perhaps easier just for the visualization. But there could be different ways to do this. The important thing is we need a way to draw new training data points for these data sets dn, right? And we do this by bootstrapping. Could do this differently, but here we do it by bootstrapping. So now we say the hypothesis space is the hypothesis space of linear models. So we only allow linear models of x. And for each bootstrap training sample, we learn one new model. So here you see 2 examples. Example 1, example 2. Of course, we will have more in the background. So as you can see, some of the data points are shared within the 2 models, but others are not. So I would say that point does not exist in the left plot, for example. Well, you can look for yourself if you find other points that are on the left-hand side, but not on the right-hand side. Important point is, with the given blue data training points, we fit a linear model. And we have this model, and here we have that model. They are slightly different, but well, that's because the train data are different. Okay. So, what we do next is we compute an average model over the different training data sets. So we have a lot of blue dashed lines here. These are the trained models, trained on different bootstrap samples of the original training data. And the black solid line is the average model. We just average all those blue dashed lines here, right? And this is then this term in the decomposition, which we will need for the bias term. So for this squared bias computation, we need that average model, which we already have. This is now this blue dashed line here. And so this is the expectation of this f hat thing. And the black solid line is the true model, f true of x. What we can do now is we look at these 8 test data points, or at the 8 test data point locations in the feature space. So here, there, 8 points. And we just compute the difference between the true model and the average model, which are these blue lines here. That's this difference. Then we square it, of course. And then we take the average over these squared differences, and that's then an estimation for this expected value. And here it turns out the bias seems to be something like 1.628. Similarly, we can compute the variance or estimate the variance of the model predictions at each. So, okay. Let me start again. For computing the variance, we look at each test data point x separately. So let's start with this one here. It really doesn't matter. So what we are interested now is the variance of these different models trained on different bootstrap data sets at this test point location minus 0.2 or something like that. And we can compute the variance here. That's some value. And we do this for all the 8 orange triangle test data point locations. Here, here, here. And then we average over these 8 test points. And this is then an estimation of that expectation, because it's the expectation over the feature space of the variance of these models, variance over the different bootstrap samples. The third part, sigma squared, we just take the true one because we know it, because we simulated it. We could also estimate it from residuals, but for now we just say we know the true error variance. Now we can stack these 3 values together. One is sigma squared from the simulation, then we have the squared bias, and then we have this variance here, and it turns out that this is 2.763. Okay, the absolute value is not that interesting. More interesting is perhaps a comparison of the bias and variance, and we see bias is much larger than the variance here. That is because the linear model is not very capable, has a low capacity, so we are quite off on average. But the different models don't vary that much if we were the training data, which means that the variance is rather small. Okay. Full stop. Now, we can compare this computation with a different computation. So we can just compute the regular mean squared error. How do we do that? We take one bootstrapped model, or one model trained on the bootstrap dataset at a time, and for each model we compute the MSE on the test dataset. Okay? MSE is just mean squared error, so we average a 2 loss. So we just well, let's say we have one model here. That's just one bootstrap iteration model. We compute the L2 loss with respect to these 8 observations here. Average these, which means then we have one MSE per model, and then we can average over all the MSEs over all these models. And in the end, this turns out to be 2.72, which is more or less the same than 2.763, right? This checks out quite well. It would be better if we would average over more models and test points. Okay, so more bootstrap iterations and more test points, larger test data and so on. But more or less, I hope I can convince you that this should be the same in the long run. Okay. So in both computations, we see the error is quite high because we are underfitted. So the bias is quite large. So what can we do about that? We can try to fit the learner with higher complexity. So we can use a high degree polynomial. Here it's a polynomial of degree 7. You see here some trained models, and well, they are quite different. They seem to vary perhaps a little bit more than the linear models, especially here on the left hand side. But let's see how the GE computation turns out. So we can do the same thing as before, compute the bias, compute the variance, put it together. Then we have a generalization error, which is in this case higher, 3.1. It was 2.7 before. Not that much difference, but what really changed is the comparison of bias and variance, right? Now the variance is much higher than the bias, so the ratio flipped from linear models to this degree 7 polynomial. Here the higher capacity learner overfits. We can try to regularize, and well, if you really do this out in practice, you should regularize these polynomials. Perhaps you already know that high degree polynomials are not really good learners. But here in that case, or not but, so it follows that here it overfits. So the MSE is even worse than taking a linear model. Just one very tiny side note, and you can forget about this in 30 seconds. We have here some side edge effect on the left-hand side. It's called a Runge effect. I will not speak about this here, so that's just an artifact of how we did the simulation exactly, and usually with a high capacity learner. We should also be able to fit here well on the left-hand side. And now you can forget about this again. So what happens if we choose something in between? So for example, the correct model complexity, which would be a quadratic polynomial, then the models would look like this. Seems better than before. And, well, it turns out bias is smaller, variance is small, and the MSE is very much smaller than before. Now both are small. We can't get below the error variance of 1. That's not possible, so 1.09 is quite good, I would say, compared to the lower bound of 1. And we see here we have a low bias, low variance, so basically we are quite good here, I would say. Okay, we already spoke about capacity and also about overfitting, and here we have a plot that perhaps you have seen a lot in different flavors, and there are similar plots that mean very different things, as you can see in the chunk on approximation and estimation error. But for now, we look at this from a bias variance perspective. So here on the x-axis, the capacity, so higher capacity on the right-hand side, and on the y-axis we have the generalization error. And what this should visualize is that if the capacity grows, the training error, this blue dashed line here, gets smaller and smaller. So we can fit the training data very well with high capacity models, which is good, but if we look at the generalization error, so the solid line here, we see that at some point it starts to increase again. So we have this generalization gap, which basically comes from this variance part, right? So we can push the bias to a very small value, but then the variance starts to grow. So we want learners that fit the training data well, but that also generalize to new data. And that's the holy grail of how to do machine learning correctly, of course. Because if you're too far on the left-hand side, we're underfitting. And if we are too far on the right-hand side, we're overfitting. And both are bad, and we want to find a sweet spot here with the optimal capacity. Here again, what I just said, high capacity will usually lead to a low bias, so we fit the training data very well, but the high capacity leads also to high variance, as you have seen in the d = 7 example, so the chances of overfitting are higher. How to find a good trade-off? Yeah, is I think one of the most important things, and you could use regularization and see the chapter regularization to this. Is a very essential concept of machine learning, because otherwise, well, you're kind of guessing around a little bit which is the best degree of your polynomial. And well, you could say that's a hyperparameter, but still with these polynomials, regularization helps really a lot. And last comment here, even for correctly specified model, the generalization error is always lower bounded by this irreducible noise sigma square, which is just, well, the noise, which is just the variance of the noise.